So. Here's the attendance form before I forget. Everyone's had the first exam. I think Lee's class just started chapter 10. Varn's class should be getting there soonish. We hope so. What's that? So yeah, so you're almost there. Yeah. Um, so yeah, we'll so I'm happy to take questions as usual, but I was gonna start with stuff in chapter 10.1, which is gonna be kind of feel like a big kind of shift of direction because we were talking about functions of multiple variables and maximums and minimums and double integral. Oh yeah, you guys probably still talk about double integrals too, though, before we get to chapter 10. Yeah, double integrals. We probably don't need to come back to double integrals. We can if we want to, but I was going to start with some chapter 10 stuff. Today is what, the 28th. Chapter 10. So before we really get into chapter 10, let's go back a bit. So I'm going to remind you of a couple things from 17b. Specifically, a differential equation. Where the derivative with respect to time of x is equal to some constant times x. There's a couple things to be aware of about this specific differential equation. It's not reading first. So what does it say? So it says that the rate of growth of x, or if you prefer x of t, so how x is growing as a function of time, is a multiple of x, or in other words, is proportional to the population size x. And you might remember that this is what immediately leads to exponential growth. So when the population growth rate is a proportion or constant multiple of population size, the population is growing exponentially because as the population gets larger, the rate that they're growing increases. We can also see this just by solving the differential equation. If I solve this differential equation, dx dt equal to a constant times x, I'm going to separate my variables. 1 over x times dx is equal to a times dt. I'm going to integrate both sides. The integral of 1 over x dx is equal to the integral of a times dt. When we integrate, I'm going to ignore the absolute value and just say that the natural log of x is equal to the integral of a, which is a times t, plus some other constant. And then if we e both sides, we're going to get e to the natural log of x equal to e to the at plus c. Simplifying a little bit, on the left-hand side, we get x. On the right-hand side, we get e to the at times e to the c. And then finally, we think of e to the c just as some new constant. Bless you. So our solution to this is that x of t, the population as a function of time, is equal to some constant times e to the at. Or in other words, the population x of t is growing exponentially. This is exactly the exponential formula for, a function. So the thing I'm going to say again, although I already said it, is basically we know that the derivative of some function equal to a constant multiple of that function essentially becomes exponential growth or decay. So this describes exponential growth. Growth specifically if your constant is positive, or decay if your constant is negative. Right? Because if A is negative, your population is changing in a negative way, meaning it's decreasing. So you've got exponential decay and exponential growth. Okay. That idea where the derivative of your thing equal to a constant time your thing is going to come back a little bit later. So hold on to that. Now we're going to remember some other things from 17b, like 2x2 matrices and finding eigenvalues and eigenvectors. I know, right? So we're going to find the eigenvalues and eigenvectors for the matrix A equal 2, -1, 2, 3, 4. This is something that you will want to be fairly fast at doing, right? Like this is going to be something you're going to do quite a few times in the coming weeks. So you want to be good at finding the eigenvalues quickly and then finding the eigenvectors without too much more effort. So here's what I think is the most efficient way of doing it. We're going to start with setting the determinant of your matrix minus lambda times the identity matrix equal to 0. As a refresher, the identity matrix is just the matrix with the square matrix with ones on the main diagonal and zeros everywhere else. Almost every time in this class, when we're talking about matrices, they are going to be 2x2 matrices. There's not a lot, but if it was a 3x3, it'd be 1, 1, 1, and then zeros everywhere else. Or if it was a 4x4, 1, 1, 1, 1 on the diagonal, zeros everywhere else. So then lambda times the identity matrix, and again, lambda just means a constant, is going to be lambda, 0, 0, lambda. Or lambdas on the main diagonal and zeros everywhere else. So then when we take our matrix minus this matrix, all we're really going to do is subtract lambdas on the main diagonal. So we're going to find the determinant of -1 minus lambda, 2, 3, 4 minus lambda. And we're going to set that equal to 0. So everyone's on board. This is our A minus lambda I. For 2x2 matrices, the determinant's really, really easy. It's just the product of the diagonal things minus the product of the off-diagonal things. So it's that times that minus that times that. So we're going to have -1 minus lambda times 4 minus lambda minus 2 times 3 equal to 0. Some of the times this is going to work out really nicely. Some of the times it's going to be really heinous. You're going to end up getting imaginary eigenvalues or eigenvalues that are not really nice numbers. They're going to be irrational numbers. So be prepared for anything here. A lot of the times they will be nice integers, but some of the times they will be less nice. Multiplying this out, what do we have here? Let's see. A negative lambda to negative lambda is lambda squared. Maybe -4 lambda plus 1 lambda is a -3 lambda. -4 -6. So we end up getting lambda squared -3 lambda -10 equal to 0. And we hope that it factors. It does. This definitely factors as lambda -5 times lambda plus 2. So our eigenvalues are, I feel like I made a mistake here because looking at my notes, I definitely have something different. Oh, I do. Well, that's fine. I accidentally wrote down a different matrix. That's totally fine. It still works just fine. So I have a slightly different matrix in my notes. No worries. My notes should have had a -3 here, but don't change it because this happens to work out just fine anyway. So we're good to go. So yeah, I will also remind you that you might have learned a quicker way. So I should finish this. So my eigenvalues are lambda equal to 5 and -2. Another way to find the eigenvalues that you might have seen before is the following. You can jump straight to saying that if you know the trace of your matrix, which we often abbreviate with the letter tau, that's the sum of the diagonals, which in this case is -1 plus 4, which is equal to 3. And our determinant of our original matrix, which we call delta, is -1 times 4 minus 2 times 3, which is equal to -4 minus 6, which is -10. You can skip doing this and jump straight to saying that we have our lambda squared minus our trace times lambda plus our determinant equal to 0, which is exactly the same equation as we have right here, right? We have lambda squared minus our trace, which is 3 times lambda, plus our determinant, which is -10, equal to 0. So you can bypass writing the determinant of A minus lambda I and all that stuff and just do it this way if you like. The one thing else, no, I won't. There's nothing good to say there. No, I take it back. I had nothing else to say. So either way is fine. They'll both get you to the same place. They both will either get you to the nice place where it's factors nicely, or they'll get you to the place where you have to use the quadratic formula. But either one of these is totally okay. So after we find the eigenvalues, how do we find the eigenvectors? Well, we do the following. Actually, there's two different ways of doing it. So, eigenvectors. Each eigenvalue will have a corresponding eigenvector. Or in other words, for each lambda, there will be a vector v such that, and this is what's special about eigenvectors, the matrix A times the eigenvector is equal to lambda times the eigenvector. So in other words, when you multiply your eigenvector by the matrix, it doesn't change the direction it points in. It just might change the length of it by a factor of lambda. That's totally special. Other matrices or other vectors, if you multiply them by a matrix, it changes the direction as well as the length typically. So we care about this. Well, we'll see why we care about it in a minute. But so to find this, to find the vector v, you can do this one of two ways. My preferred way is doing this. Start with this equation. Start with A times your vector that you're trying to find equal to lambda times your vector. So our equation, our matrix A was -1, 2, 3, 4. We're trying to find the vector v, which I like to call xy. Other people call it v1 or v2 or x1 or x2 or whatever. Equal to, let's pick which eigenvalue. Let's say we're gonna do it first for lambda equal to 5. Usually I like to label my eigenvalues as lambda1 and lambda2. It doesn't matter which one you call which, but it's pretty common practice to say that lambda1 is the larger positive value of the two. If they're both positive, it's the bigger one. If one's positive, it's that one. They're both negative, it's the one that's less negative. It doesn't really matter though, but that's the convention you'll typically see. Sorry, 1 second. Let me pin my video here. Sorry. Okay, so this is supposed to equal the eigenvalue 5 times the same unknown eigenvector that we're trying to find. So here's my A, here's the vector v, here's my lambda, there's the vector v again. Most of the time, to figure out what that vector is going to be, you only need one of the two equations that this matrix equation represents. So I'll point out, there's two equations in this. The first equation, again, come from the top row, is -1 times x plus 2 times y equals 5 times x. That's all we need, really. I'm going to write the other equation as well so you see it, but we don't actually need it. The other equation is 3 times x plus 4 times y equals 5 times y. And what is true most of the time with these is that they both give you the same relationship between x and y. If you isolate y in either one of these, well, in this first one, if I solve for y, I'm going to get 2y equal to 6x. Divide both sides by 2, I'm going to get y equal to 3 times x. Or in this equation here, I'm going to subtract 4y and get 3x equal to 1y. Oh yeah, they both give me the same relationship between x and y. So you don't need both equations. What you do need to do is be comfortable then just saying, I'm going to pick x equal to this number. What number? Any number except for 0. Because the only choice that is not a valid choice for an eigenvector is the 0 vector. So we don't want 0, 0 ever. Never, ever, ever. Any other choice is fine. It's okay to have 0, 1 or 1, 0 or something not 0, something not 0, but 0 and 0, no dice. So in this case, I would say I'm going to pick x equal to any non-zero number I like. I'm going to pick 1. The standard choice is pretty much the smallest possible integers you can pick. So one choice for my eigenvector would be that x is equal to 1 and y is equal to 3 times 1. You could also have made any other non-zero multiple of that as your choice. So the vector 2, 6 would be equally good, or -3, -9, or -100, -300. Any non-zero multiple of your eigenvector is also an eigenvector. It's pretty standard to, again, pick this one, but it's okay to make a different choice. And it's totally correct to also make a different choice. I'll point out this eigenvector fits the bill. If you actually multiply -1, 2, 3, 4 by the eigenvector 1, 3, we're going to get, let's see, -1 times 1 plus 2 times 3 for the first entry, and 3 times 1 plus 4 times 3. That ends up giving me 5, 15, which is exactly 5 times the original eigenvector, as expected. You never have to check this if you've done the work correctly, but it's nice to see that it's actually right. So I would say doing it this way, meaning the matrix times the vector that you're trying to find equal to the eigenvalue times the vector you're trying to find, is my preferred way of doing it if the eigenvalues are nice. If it's an integer. If it's anything, I mean, a fraction, fine, but usually an integer. If it's anything that's irrational or imaginary, I actually usually like to do something else typically. So the other way to do this, and we'll use the other eigenvalue, or to find v, we can solve, instead of solving a times v equal to lambda times v like we did up here, we're going to essentially subtract lambda times v to the other side and say we're going to solve a minus lambda times I all times v equal to the 0 vector. I can't just say it's a minus lambda because A is a 2 by 2 matrix and lambda is just a number. So to make that subtraction work, I say, oh, it's A minus lambda times the identity matrix. And then I'm doing a 2 by 2 matrix minus another 2 by 2 matrix. So here's what we're trying to solve this time. It's going to be our matrix A, which is -1, 2, 3, 4. And our lambda, our second eigenvalue here is lambda 2 equal to -2. Just want to check one thing here. Yeah, okay. So instead of doing this minus lambda I, well, actually I'm doing that. So minus -2 times the identity matrix. Again, I would normally skip that step. All of that multiplied by the thing we're trying to find should equal the 0 vector. This looks like a little bit more work. It usually is a little bit more work. So let's do our simplification here. So we're going to have, let's see, -1 plus lambda. Oh, I need to plug. I know. I was like, what am I? I'm doing something weird. I forgot to plug in the -2 for lambda. Sorry. That should be a minus -2. That's what I was like, you're doing something screwy, James. So let's see what we got here. We've got -1 minus -2, which is -1 plus 2. We have 2 minus 0. We have 3 minus 0. And we have 4 minus -2. times the vector xy equal to 0, 0. So I'll point out again, I just took my matrix A and I subtracted -2 or whatever the eigenvalue was from each of the diagonal spots. -1 minus -2 is +1. 4 minus -2 is 6. And if you look at these equations, they're pretty much the same, right? That first equation is 1 times x plus 2 times y equals 0. The second equation is just the same equation multiplied by 3. But both equations here are 1 times x plus 2 times y equals 0, or 3 times x plus 6 times y equals 0. But either way you look at it, you're going to get the same relationship between x and y. So here we're going to get x equal to -2y, or not, right, same deal down there. So here, and here's how I really do it, to be perfectly honest. My second eigenvector, here's the way I like to do it. I like to pick x and y to be the other variable's coefficient. So in this equation, where I have 1 times x equals -2 times y, I'm picking x equal to -2 and y equal to +1. Because it works. If x is -2 and y is +1, yeah, 1 times -2 equals -2 times 1. So it totally works. And that's usually the easiest way to see it, I think. So if you have something like 3x equals 5y, instead of being like y equals 1 and x equals 5/3 or something, just pick x equal to 5 and y equal to 3, and then it totally works. And you've got the nicest kind of way of doing it. So our eigenvalues are λ1 equal to 5, with the eigenvector being 1, 3, λ2 equal to -2, with the eigenvector being -2, 1. Anything else I wanted to say here? I will just go back and say, I usually, again, I like doing it this first way better, like where you do A times your vector equals λ times your vector. To me, that just makes more sense. But either way is totally fine. And again, this second way of doing it is better if your eigenvalue is less nice. We'll see that eventually. What else do I want to say here? All right, so the reason we're talking about all this is because we're now going to try to set up some equations for a linear system of differential equations. So let's look at this first example here. Don't worry, we're about to use both of the things we just talked about. So, if I use the wrong matrix, that's okay. So, an example. We're going to let x1 of t equal a population of predators at time t. You might think of wolves. And x2 of t is a population of prey at time t. You might think deer. And then we're going to say that the derivative of x1 is equal to the rate of growth of your predator, of your predator's population, rate of growth of predator population. And similarly, the derivative of x2 is your rate of growth of your prey population. And we would kind of expect that these populations depend on each other, right? If there's more wolves, they're probably going to kill more deer. So the deer's growth rate is probably going to slow down. The wolves' growth rate is going to increase, but then there's going to be too many wolves, not enough deer. So then wolves will die because there's not enough food. And then less wolves will mean there's more deer. And it's kind of like the cycle is going to go back and forth. The way we're going to think about this one in this case, and this is where I'm regretting the matrix choice I made, but it's fine. We're going to say that the rate of change of the wolf population size is equal to -1 times the number of wolves plus 2 times the number of deer. So the way I'm kind of reading this is if there's, right, the more wolves there are, the less good that is for the wolves trying to survive because there's less prey to kind of spread out between them. Whereas the more deer there are, the better for the wolves because there's more to eat. And similarly, we're going to say that the rate of change of the deer population size is equal to -3 times x1 plus 4 times x2. So we're saying the more wolves there are, the more the deer population is going to decline, right? 'Cause the rate of growth is going to decrease if there's more wolves. And then the more deer there are, that's good. They're going to increase in population size because they can make more deer. Yes, I know this is kind of a simplistic, right, idea here, but we're just trying to kind of get the point across here. Like, oh yeah, these things depend on each other. We're also going to say that the initial population of wolves is 2 or some maybe 2,000, and the initial population of deer is 4. Let's say in the thousands, just to make it seem slightly more realistic. All right, so now here's what we're going to do. We're going to solve this system of differential equations. And unfortunately, yeah. What did you do here? Sorry, I'm something. I feel like I think I killed a page of notes here, and I've not that I can't do it without them. Just want to make sure I'm not forgetting to say something I mean to have said. There we go. Okay, yeah, there we go. So here's how this linear system of differential equations can be rewritten. This looks like, I should write the words, this linear system of differential equations. Linear because each variable is only raised to the first power, not squared, not square root, nothing funky like that. And differential, obviously, because we have a derivative equation equal to something based on the variables. This can be expressed using a matrix. We can express it as dx1 dt, dx2 dt is our derivative vector equal to the matrix -1, +2, -3, +4 times the population vector x1 of t, x2 of t. The same equation, just written with matrices. Or if you like, you can think of this as, if you like, the derivative of your population vector equal to your matrix A times your population vector. Or as I would like you to think of it, your derivative of your thing equal to essentially a constant times the thing. And we started off this conversation saying, oh yeah, if you have the derivative equal to a multiple of your thing, then your solution is that we have exponential growth or decay. But it's kind of funky here, right? Last time we said, if your derivative is equal to a times x, you end up getting the x of t is equal to c e to the a times t. But you can't really take e to a matrix, right? It wouldn't make sense to say that if dx dt equals capital A times the vector x, are we thinking that x of t is equal to e to the a times t? That's a little bit weird. Well, here's what we're going to do. Instead of raising things to the power of the matrix, we're going to use the stand-ins for the matrix. The eigenvalues essentially get to play the role of the matrix because I'll remind you, right, multiplying your matrix by your vector is a lot like multiplying your matrix by your eigenvector, or your eigenvalue by your eigenvector. So if this is an eigenvector, then we can kind of say, oh, we're going to use the eigenvalue instead of the eigenvector. We're going to use the eigenvalue instead of the matrix A. Sorry about that. I misspoke there. Right. So essentially, if the vector, and this is a big if the vector that's representing the populations at time t is an eigenvector, then we can say that this derivative equal to the matrix times your eigenvector can be solved by something like x equal to a constant times e to the lambda t instead of e to the a times t. And that makes sense, right? Lambda is just a number. It's not a vector. It's not a matrix. So this idea is totally sensible. Here's how this actually ends up working out. Our solution to this system, our general solution to the system of differential equations, dx as a vector, dt equal to a times x as a vector, looks like the following. Your solution vector, your populations at time t are going to be the following. Some constant times e to the first eigenvalue times t times your first eigenvector plus some other constant times e to your second eigenvalue times t, times t times your second eigenvector. So it's essentially like this solution idea, except since there's two eigenvalues for each matrix and two associated eigenvectors, we have to break it up into two parts to get that whole sort of thing going on. But this totally is a solution. And yeah, we have enough time. Cool. So unfortunately, I used a slightly different matrix when we started this process. So we're going to have to take this matrix equation, which I forgot to write the initial conditions here, where x1 of 0 is equal to 2 and x2 of 0 is equal to 4. And we're going to find the solutions for this system. It's kind of neat, I think. So we're going to do the same process we did before. We're going to start by taking our matrix A, and we're going to find the eigenvalues and eigenvectors, and then we're going to jam everything in to this solution right here. And again, the reason we know we get to do this is because we know that your differential equation, where your function equals a multiple, sorry, the rate of growth equals a multiple of your function, which is essentially what this is represented by exponential growth. So we know we can jump from this to something like this because of that relationship. It's not exactly a direct correspondence, but it's close enough that that's why we're talking about it, right? It's like, okay, it seems plausible. So let's find the eigenvalues. So we're going to take the determinant of our matrix minus lambdas in the diagonal. So -1 minus lambda, 2, -3, 4 minus lambda, and set that equal to 0. So here we're going to have -1 minus lambda times 4 minus lambda minus 2 times -3 equal to 0. Multiplying this out, I'm always going to write lambda squared first. You're always going to have a lambda squared. Negative lambda times negative lambda is lambda squared. And I have a -4 lambda plus lambda is a -3 lambda. And a -4 plus 6 is +2. I will point out, just so everyone can see it, -3 is equal to the trace of that matrix. Sorry, is equal to the negative trace. 3 is the trace, -1 plus 4. And +2 is the determinant of that matrix. -4 minus -6. So you could do it that way if you wanted to. And then factoring that, it looks like we ended up getting lambda -2 times lambda -1 equals 0. So our eigenvalues, kind of confusingly, are lambda 1 equal to 2 and lambda 2 equal to 1. Because again, I'm going with the convention that we say that lambda 1 is the bigger of them. Again, not super duper important, but if you want to do it that way, it's usually a good idea. Okay, so let's find the eigenvectors. So for lambda 1 equal to 2, we're just going to take our matrix, -1, 2, -3, 4, multiply it by the vector, and set it equal to 2 times the vector we're trying to find. You know why I think I like doing it better this way? I don't have to subtract 2 from my diagonals in my matrix. I think it's much easier to be like, okay, cool, my matrix is A, I'm multiplying by something, it's equal to my eigenvalue, which is multiplied by the same vector. That's much easier to write down than saying, let's see. I mean, it's not that much harder, but I'm like -1 minus 2, 2, -3, 4 minus 2, plus you. Let's do it again. So you could do it either way. I just feel like this second way takes more thinking and it's easier to make a mistake. So I'm going to do it this way because I like it better this way. And then I'm only going to write down the first equation. -1 times x plus 2 times y equals 2 times x. I'm going to add x to the other side and get 2y equal to 3x. And then I'm going to take the easy solution and say that my eigenvector is going to be, x is going to be how much? And y is going to be how much? Right. Easy peasy. You could do other things. You could solve for y and say y equals 3 halves x, and then pick x equal to 1 and y equal to 3 halves. Or you can make other choices. Not what choice? What are we not allowed to have? Right, the zero vector. You can have a coordinate being 0, though, just not both. Okay, same deal for lambda 2 equal to positive 1. We have negative 1, 2, negative 3, 4 times xy equal to 1 times xy. Again, using the first equation, negative x plus 2y equals x. Adding x to both sides, we get 2y equal to 2x. I would reduce both sides to say y equals x. So we end up getting the eigenvector being just 1, 1. Okay. So now we get to say the following. I don't know if you remember, but the reason this works is because back in 17b near the end, we talked about how you could write your kind of initial vector as a linear combination of the eigenvectors, and that's always something you can do. So really the idea is whatever your initial is, you're kind of thinking of writing that as a linear combination of these eigenvectors, and then the matrix multiplication works out super nicely. That's why we're doing this. Here's our solution. I highly recommend remembering that your solution should look like C1e to the lambda 1t times V1 plus C2e to the lambda 2t times V2. You only have to remember one thing, the first part, because the second part is just the same thing with different subscripts. So in this case, our solution, x of t, which I wouldn't usually write, but sometimes would write as x1 of t, x2 of t. Again, wolves and deer is equal to C1 times e to the lambda 1 times t times my V1, which was 2, 3, plus C2 times e to the lambda 2 times t, which is 1 times t, times V2, which is 1, 1. So a couple ways to look at this. Yeah. I usually like to leave it like this. Oh, I'm sorry. That's not what I'm saying yet. Not there yet. We still have to then, well, not always, I would say this is the general solution. And since we were given initial conditions, whenever we have initial conditions, that means we can solve for those unknown constants. So our initial condition was that x1 of 0 is equal to 2, x2 of 0 was equal to 4. So we're going to plug in 2, 4. Wow, that's a 4, sure. 2, 4 for that, and 0 for t. So we're going to get 2, 4 equal to C1 times e to the 0 times 2, 3 plus C2 times e to the 0 times 1, 1. So we have two equations. Our top row equation is 2 equal to C1 times 1 times 2 plus C2 times 1 times 1. And my second row equation is 4 equal to C1 times 3 plus C2 times 1. There's lots of ways to solve these things. In my opinion, the easiest way to solve this one would be to subtract the second equation from the first one, because those C2s will eliminate. If I do this equation minus that equation, 2 minus 4 is negative 2. 2 times C1 minus 3 times C1 is negative C1, and C2 minus C2 is 0 C2. So I end up getting C1 equal to positive 2. And I can plug that back into either equation. Let's plug it into the top one and say 2 equals 2 times 2 plus C2. Subtracting 4, we get C2 equal to negative 2. So my specific or particular solution is that x of t, which is equal to, again, x1, x2, is equal to 2e to the 2t times 2, 3 plus negative 2e to the t times 1, 1. what that also means is that we can say that the population of wolves has the following population model. X1 of t equals the top row, 2e to the 2t times 2 minus 2e to the t. And the deer population is going to look like 2e to the 2t times 3 minus 2e to the t. Both of them are going to get larger and larger and larger because this part is going to outweigh that second part. A couple things to say about this. I do want to make sure I say these things correctly here. So it's not a particularly interesting question at first, but if you just ask, what happens as time goes on, what happens to the wolf and deer populations as time goes on, well, they're both going to get infinitely large. The limit as t goes to infinity of 4e to the 2t minus 2e to the t. If it's harder to see that this one's going to outpace that one, you could also just factor out an e to the t and say you have e to the t. There should be a limit in front of this, James. You have e to the t times 4e to the t minus 2. And then it's a little easier to see that, oh yeah, that's going to infinity, that's going to infinity, and infinity times infinity is infinity. In a similar way, the deer population is also growing infinitely large. Again, this is right. I mean, not really. Other constricting things would eventually come in and make a difference. But if you just base the model on what you have here, we would expect the population to be infinitely large. Which means probably not a great model if it's going to say we have infinite deer population eventually. But here's the more interesting thing to talk about, and the thing that we actually kind of care about. Where'd you go? Sure. The more interesting thing is, what's the ratio of wolves to deer doing as time goes on and on? So what about the wolf to deer ratio? Well, if we take the limit as t goes to infinity of the wolves divided by the deer, well, when you have a limit like this, we typically try to divide everything by the thing that's growing the fastest to see what's happening. Kind of like with rational functions, how you divide everything by the highest power of x. Same idea here. E to the 2t is growing the fastest. If we divide everything by e to the 2t, look what happens. We get 4e to the 2t divided by e to the 2t, 2e to the t divided by e to the 2t, 6e to the 2t divided by e to the 2t, 2e to the t divided by e to the 2t. If we rewrite that, we get the limit as t goes to infinity of 4 minus 2 over e to the t over 6 minus 2 over e to the t. The 2 over e to the t's get really, really small. And so our ratio of wolves to deer is 4 to 6 or 2 to 3. Which is exactly the ratio in the eigenvector associated with the larger eigenvalue. The ratio of the eigenvector with the larger eigenvalue. I should say the larger positive eigenvalue. So they're both negative, you don't really see what's happening. Or they both get, if both eigenvalues are negative, the populations eventually both go towards 0. Because if you have an equation like this, if both of those are negative coefficients of t, then sorry, I'm just seeing, oh yeah, if both of those were negative instead of positive, either the negative something gets smaller and smaller and smaller as time goes on. So they both go towards 0. It's not happening here, but just for future reference. One other thing I wanted to say about this. Yeah. Oh, actually, how much time? Yes, we can. Okay. So I will point out this really is a solution to our original system of equations, right? If you look back and say, oh yeah, our system was that dx1 dt is equal to, I forgot what it was, to be honest. Apologies. -1 times x1 plus 2 times x2, and dx2 dt is -3 times x1 plus 4 times x2. And our solutions are that x1 of t equals 4e to the 2t minus 2e to the t, and x2 of t is equal to 6e to the 2t minus 2e to the t. We can actually show that both of these equations are true. If you take the derivative of x1, well, my derivative of x1 is going to be the derivative of 4e to the 2t minus 2e to the t, which is equal to 4e to the 2t times 2 minus 2e to the t times 1. And then if you actually calculate the right-hand side of this equation, negative x1 plus 2x2 is equal to negative 4e to the 2t minus 2e to the t plus 2 times 6e to the 2t minus 2e to the t. That's negative 4e to the 2t plus 2e to the t plus 12e to the 2t minus 4e to the t. And that's going to be negative 4 plus 12 is 8e to the 2t plus 2 minus 4 is minus 2e to the t. And that's exactly the same as that up there. So it really truly is true that the derivative of x1 is in fact equal to negative x1 plus 2 times x2. And in a similar way, you all could and should show that the derivative of x2 is exactly equal to negative 3 times x1 plus 4 times x2. So that's the gist of what we're going to be doing for the next couple of weeks, is taking systems of differential equations like this and solving them by finding the eigenvalues and the eigenvectors of the matrix, and then writing the solution as C1 e to the lambda 1t times V1 plus C2 e to the lambda 2t times V2, and finding the constants if we have initial conditions. And then we'll talk more about that, because there's more to say about like what the eigenvalues mean as far as the whole system. And I'll just point out lastly here that this system of differential equations can be represented by a direction field. So this direction field here is actually what this linear system kind of looks like. So if you plot, like for example, if you plugged in an initial condition of say like, well, x1 equal to 2 and x2 equal to 4, you're starting right there. And look, you're just getting bigger and bigger and bigger for both the x's and the y's. But if you started somewhere else, like over here at x1, well, negative is not really, like x1 equal to 1 and x2 equal to 4, well, then you're on this downward trend this way. So depending on where you start, you can have a totally kind of different eventual thing that happens, because your initial conditions might make things very different. But that's kind of the idea, is that this kind of represents all the different starting places you can have once you start somewhere, kind of the trend line of which way you go. Yes. So the x1 of t and x2 of t are the, sorry. So if you look at your general solution here, like right here, where I wrote as C1 e to the lambda 1 t times V1 plus C2 e to the lambda 2 t times V2, the x1 is just the top row. So it's this constant times 2 plus this constant times 1. And the x2 of t is just the bottom row. It's this constant times 3 plus this constant times 1. I could have written it as one vector, as like 2e to the 2t times 2 plus negative 2e to the t times 1, and the second row being 2e to the 2t times 3 plus negative 2e to the t times 1. Like that. You're welcome. We'll continue to talk about this on Wednesday. Yes, what's up? Yes. Okay. So there really isn't anything to be done about that. So the way this class works is I take attendance in person, and whether or not people join late, you're responsible for coming at least 70% of the classes that
Yeah, from then on, right?
from the beginning of the class.
So even
Right, because I've had students in the past who have dropped the class and then joined back in so that they could have started later to kind of affect this. I'm not saying that you would do that,
Yeah.
but the policy is what it is because I don't want to have to say some things for some students, some things for other students. The policy is blanket policy, what it is.
Okay. Okay.
You're welcome. You're welcome.